Hi, Ron. Hello. Yeah. So the Google so this the website is hosted by Google. It's a Google site, so you can probably tell after you type in mathbennett.com, it says something like sites.google.com/wsd1 or whatever. So that's free, and yeah, I paid for the domain. Domains are depending on the type of domain. The domain that I chose was $10 a year, which is pretty cheap. Um, Most domains are $10 a year, but some domains are a little bit more. Like I think that if you have like one of those, like, I don't know what you call them, like Web 4.0 domain names, like like Maya.cool or something, or like one of those weird dot extensions. What are those called? Uh, I forget what you call the end of a domain name. But anyways, if you choose one of those, then it can be quite expensive. Or if there's a domain name that is like really popular, then it'd be very difficult to purchase or just very expensive. Like if you tried to buy google.com, you'd have to spend a lot of money. So it depends on the actual domain, but no one wanted mathbandit.com. So I got it for $10. I have heard though, what sometimes happens is some people will have a domain name and it's like $10 a year and who cares? Like no one is really concerned about it, and then they, maybe it's like someone has like a hobby, like a photography kind of hobby kind of thing, and then they forget about their website for like a year or something. Then what often happens is that these companies will find these domain names and purchase them, kind of preying on these people wanting to spend lots of money on their domain to get it back. So yeah, domains can cost all sorts of amounts of money. hmm Yeah. So maybe you can not go to university and just buy some clever domain names. I think there's that really famous guy. I think his name is actually, he changed his name to Kim.com. Do you know that guy? Have you heard of him? You should look him up. He's a really interesting guy. He's very eccentric. I think he's either in jail or something. He's the owner of uh, what is it? Mega Upload, like one of those sketchy. Is he the owner of Wish.com? Oh, yeah. I wouldn't be surprised. I think I got it. It's a sketchy website. Um, anyway, yeah. So he's like the owner of Mega Upload, which is a website that's well known for piracy and hosting kind of illegal files and things like that. Anyway, he made millions and millions of dollars by purchasing domain names back in the 90s. Yeah, he is. Yeah, I think you're right. I think he is out again. And yeah, Mega Upload. Yeah, it has got shut down. But I think that there's other similar websites like Mega.com. I don't know if. Yeah. And I'm not sure if Kim.com has any kind of association with that. But from what I understand, he's made a lot of money by purchasing um, domain names at the right time, and kind of playing that market. It's almost like it's its own stock market in a weird way. Like you can kind of purchase these random domain names in hopes that someone else will purchase them. But um, lucky for me, no one wanted mathbennett.com. But yeah, no, domains are usually $10 a year, so they're usually quite cheap. And I got my domain from Google as well. So I tried to keep everything, like I tried to keep everything that I do with school, all associated with my Winnipeg School Division account, just so there's no sort of, I don't know what I'm trying to say. It's all kind of in one package. But I probably could have, but it was like $10. It's probably more trouble to put it on my budget and. But yeah. That's a good point. Maybe I should submit my receipt now that I think of it. Yeah. Is it? Okay, cool. Yeah, it is nice to have your own domain name for emails. I used to have the domain, which it's probably been purchased now that I kind of gave it up. But I had maxben.net, so it was kind of like my name, like Max Bennett. And then I had the coolest email. It was max at maxben.net. And then but it was so confusing because no one knew. Like, I would say my email and people would be like, what? And I'd have to like spell it out letter for letter. So in the end, it ended up being a very, very bad email address because no one understood what I was saying. Really? Are you serious? Yeah, there you go. See? Yeah, maxben.net. Yeah, it's $2,600. That's crazy. Well, that's why they're doing it. Because they probably because. Absolutely, yeah. Because I had maxben.net for a couple of years, and then I guess I just gave it up, and then now they're probably hoping that I'll buy it back for $2,600, which I won't do. I'm not that interested. Yeah, yeah. I'll consider that. Or 24 monthly payments of 109. That's not too bad. Okay, looks like there's a few people here, so that's good. What do we have? 7 people on Discord and 1 person on YouTube, so that's great. I'm going to talk about a couple of things today. By the way, that feedback form is on the website, so I recommend that you fill it out because I'd like to hear from you about what we can do going forward. So I had a special part of the form just for you guys because I have some questions specific to you, in particular about what we can do for the review. I mean, I have some ideas, but I'd like to hear from you about what you think would work well for the review, and then also for after the AP exams, what kind of thing are you interested in? I'm thinking. I'm thinking mostly of doing like a project which would eventually end up as some kind of essay format kind of thing, some kind of report or an article. And there's many different sort of ways that could look, even in and of itself. I thought maybe we could do some presentations too. I think that a lot of us have the technology for that. Not all of us do, but it could be sort of an optional thing. So that's another thing we could do. And finally, there's a third option, which is just something that you could suggest. So if you have an idea of some kind of learning that you'd like to do after the AP exams, I'd love to hear from you. Yeah, maybe we could do your suggestion, and that could also just be, you know, your own thing, or maybe it could be something that the rest of the class would want to do as well. So I'd like to hear from you guys. Go ahead. Oh, yeah. The polar coordinates. You know what? I haven't fully decided. We could continue doing the polar coordinates after the exam. If you're interested in that, then let me know. I mean, really, this is more about you than it is about me at this point. So as far as I know, it's not going to be on the exam. According to the AP College Board, polar coordinates will not be on the AP exam. Yeah, okay. I mean, I'll double triple check. I mean, I've looked a few times, but as far as I know, polar coordinates are not on the exam. So if you'd like to do polar coordinates, then let me know. That could be, you know, you could include that in your other suggestion. Did you have something to say? No? Okay, never mind. I just saw your microphone button. By the way, they're cutting down trees on my street, so if you hear some buzzing, that's what that sound is. Okay, yeah, so fill out that form. There's also just a whole bunch of questions that I'm asking everyone, not just AP students, but you know, just things about like, are the lectures engaging? Like, is there anything that I can do to change that? How is the workload and that kind of thing? So yeah, let me know what you think, because I'd really like to hear from you, because we still have a lot of time left in the year. Like, it's not like the year is over. We still have, you know, several months. So I'd like to sort of plan around how this is working out for you. So let me know. Okay, a couple things that we're going to talk about today. We're going to talk some more about sequences and series, and how they converge, or maybe they don't converge. So let's talk about convergence and divergence. So, I don't want black. How about blue? Okay, so we're going to talk about convergence, and divergence. Okay, so convergence, really all convergence means is, in an infinite something wrong? Okay, yeah, my iPad kind of glitched out for a sec. So convergence means that in an infinite sequence, the nth term tends toward a value, I should say a well-defined value, as n approaches infinity. Okay, so for example, we could say that something like if an is equal to 1, how about, let's say if 3 plus 1 over n, so that approaches 3. So as n approaches infinity, an approaches 3, because we basically would be adding a smaller and smaller amount to 3 until finally we just get to 3. I mean, we would never actually get to 3. We're always going to have a little bit extra, but you get the idea that we'll eventually get to 3. So that's what it means in terms of a sequence. I want to talk a little bit about what that looks like for a series. So before we do that, I need to talk a little bit about what a partial sum is. So let's talk a little bit about series really quick. So series. Okay, and I think we've looked a little bit at summation notation. So a series, as I think we spoke about this last class, or maybe even last week as well. So a series is the sum of a sequence. Okay, and the notation that we use this nice big capital sigma, and we have an index. So usually we'll have something like n equals 1, and then let's say that it's going to go until m. So this would be, if we went from n equals 1 to m of a n, that would be a1 plus a2 plus a3 plus all the way, and then finally we would stop to am. Okay, and this is what we would call a partial sum. Okay, it's a partial sum because we're not going all the way to infinity. Okay, so if I wanted to, I could say that the infinite sum is this. We would go from n equals 1 to infinity of an, and the way we consider that is we would say that this is the limit as n approaches, or sorry, m rather, because m is kind of our stopping point, as m approaches infinity of the sum from n equals 1 to m of an. So basically we think of these partial sums, we think of this, so these are kind of like the terms in a sequence. Okay, and an infinite sum converges if the sequence S1, S2, S3, and on and on and on converges. You might be asking, well, what's S1, S2, and S3? Well, where Sn is equal, actually I should use the letter m. I keep getting confused between n and m here. So where Sm is the partial sum from n equals 1 to m of a n. So the idea is that we're thinking of these partial sums as terms in a sequence, and I think we understand what it means for a sequence to converge, because it'll actually end up equaling a single point. But when it comes to an infinite sum converging, it's a little more complicated, because it's hard to imagine continually adding terms to a sequence, or continually adding one term after another and then getting a finite result. So you've got infinite terms but a finite sum. But it happens quite often, and it's really not as hard as you might think. So let's just talk a little bit about different types of series and when they're going to converge and when they're not going to converge. So I think we talked a little bit about arithmetic series. So arithmetic series. Okay. So in arithmetic series, these never converge. They always diverge. Okay. So remember, an arithmetic series, there's a common difference between terms. Okay. Okay, so it doesn't matter how small that common difference is, you're always going to get infinity. It doesn't matter how small you're adding each term, you're always going to get, well, either positive or negative infinity. Well, then it wouldn't be an arithmetic series, because there would be no common difference, right? So there'd have to be a non-zero difference. So, but you're also asking, okay, I mean, that's not actually an obvious statement. So if you're on YouTube, you might be you missed it. But one of the questions was, well, what happens if we're going from I equals 1 to infinity of 0, and then the common difference is 0? Well, this is kind of like saying this is like infinity times 0. What's that? Yeah, we'd have to attack it with L'Hopital. That is not immediately obvious what that's equal to. So I'm just gonna put a little question mark behind there and let you think about that one. Well, I mean, we saw before that, what was it, 1 times 1 times 1 times 1 times 1 is not equal to 1, always, right? So it could be, I don't know, I mean, it seems like it would be 0, but maybe not. I mean, long story short, it's 0, but it's not immediately obvious to me why it is 0. So let's talk a little bit about, okay, I should actually do an example of an arithmetic series. So here's an example of an arithmetic series. So let's think of a very small number, like let's think of 2. Okay, so yeah, we're going to be going up by 2s. So we'll have 2 times n, and then we'll go from n equals 1 to infinity. And you can immediately see that this thing is going to get really big really quick. So the first, no, it is not geometric. This is arithmetic. Yeah. So because there's a common difference because we're multiplying it. A geometric one has a ratio, which means that you're multiplying it by n each time. So in other words, you're repeatedly multiplying, or there's an exponent. So you'd have 2 plus 4 plus 8 plus 10 plus, and this thing just blows up really, really quickly. So this goes to positive infinity. So that's no good. That's not really interesting. We don't really talk a lot about arithmetic series in calculus because their infinite sums are pretty much always, well, not pretty much always, but always either positive or negative infinity. There's not a whole lot to say about them. So let's divert our attention to and another thing that I want to point out. Like, and we'll talk about this in a little more detail later. But look at the terms. The terms are getting bigger as we go, right? Like we're going from 2 to 4. Like eventually we're going to be adding, like the terms themselves are going to be approaching infinity, let alone their sum, right? So in order for a series to converge, so in order for the series sum from n equals 1 to infinity of an to converge, we need that the limit as n approaches infinity of an, so just the sequence, not the sum, but the sequence of the terms, we need this to be equal to 0. So the terms have to be approaching 0, right? Because we're adding them all up. So if there's going to be any kind of meaningful sum to this, well, at some point we better be adding something that's so small that it's not really going to be affecting the sum at all, right? Because if we're adding like 3 plus 3 plus 3 plus 3 plus 3, like something that's not 0, and you're adding it infinitely many times, then you're going to get infinity, right? So it's going to blow up. There's going to be no bound to it, so it's going to grow without any limit, right? So it's going to go to either positive or negative infinity. So we need that the terms themselves have to be approaching 0. So the terms have to get smaller. That's one of the requirements, okay? So I'm just going to write that again. So a requirement for convergence, is that the limit of the terms must approach 0. Now, It's not an if and only if statement. That's right. So we'll talk about how this is a requirement. It's what we would call So this is a condition, but it's not sufficient. So what that means is that just because the limit of the terms equals 0 does not mean that the sum converges either. So we'll look at a few examples that illustrate that in just a second. But let's talk a little bit about geometric sequences really quick. Or sorry, geometric series. So let's talk geometric series. Okay, so geometric series, these ones are really nice because these ones can converge. These ones can converge. And we saw that, I think it was the Zenos Paradox the other day. So I want to quickly talk about what a geometric series looks like. So a geometric series looks something like this. We have, we'll go from n equals 1 to infinity. And let's say that our first term is just a. Our first term is a. And then between terms, you have a common ratio. Okay, so the common ratio we usually, actually let's get rid of those brackets. The common ratio we usually refer to as r. And each time we multiply by r, so we're going to go, we're going to increase the number of times we multiply by that ratio, and it's equal to r to the n. So our terms look something like this. We'll have a times r to the power of 1. If you wanted to, you could say that this starts at 0, and really all it does is it just changes that first term. Either, it's still a geometric series because the ratio between the terms is still going to be constant. The next one is going to be a times r1. The next one after that will be a times r2 plus ... And I guess it goes on forever, so there is no last term. So that's what a geometric series looks like. And this converges whenever, actually, why don't I say this converges if and only if the ratio, or the absolute value of the ratio, is less than 1. Okay, so as long as your ratio is less than 1, or the absolute value of the ratio is less than 1, then your ratio, then your series converges. So can the ratio be equal to 0? Yeah, it would converge, but it wouldn't really be a geometric series anymore, right? Because if it was a geometric series, then okay, because let's say that it was 0. So first of all, we'd have a problem right here, right? A times like 0 to the 0. Well, immediately we have a problem. But ignoring that, let's just say that's equal to a. Then we'd have a times 0 to the 1 plus a times 0 to the 2 plus ... So our terms would look like this. It'd be a plus 0 plus 0 plus 0. So you'd say, okay, well, what's the ratio? What's the ratio? Okay, well, sure. The ratio between these two terms would be 0 over a, which is a. Great. Oh, sorry, not a. It's 0 over a is 0. Perfect. So that means the ratio must be 0, right? Well, what about the ratio between these terms? 0 over 0. What? So not a geometric series. Does it converge? Yes, it converges. It converges to a, right? We get a well-defined sum, but it is not a geometric series. So technically, yes, it converges, but technically no, because it's not a geometric series. So whatever that means. Okay, so let's take a look at an example. I should actually give you the formula, and this is a formula you're going to have to memorize, and it's a formula. Pardon me? Or you can derive it. Yeah. It actually isn't too bad to derive. You can basically derive it by looking at how you would calculate the ratio. I derived this formula in both of my grade 10 advanced and my grade 11 pre-calc classes. So it actually would be a good exercise to try and derive this. It's really not that bad. So yeah, the way we would have this, so the formula is, let me make this look really nice. So the formula is the sum where n goes from 1 to infinity of a times Rn. So that would be a geometric series. So let's call this an infinite geometric series. Okay, this is equal to a over 1 minus r. Simple as that. So that is that's our formula that we have to memorize. So it's really not that bad, right? It's so you take your first term, right? So this is our first term, and actually this should be 0. Pardon me. Otherwise, this wouldn't be our first term anymore. So you take your first term and divide it by 1 minus, that's supposed to say minus the ratio. So it's actually a fairly simple formula. You just take your first term, divide it by 1 minus the ratio. So let's do that example from Zenos Paradox and see if it still works. So Zenos Paradox was about adding a half plus a quarter plus an eighth plus yada yada yada. So what we could do is we can say that, all right, well, our first term is 1/2, right? Because we're starting off with a half, and the ratio between terms is a half. Okay. Oh, and that's supposed to be to the power of n. There we go. So where n goes from 1 to infinity, or sorry, 0, I keep doing that. Where n goes from 0 to infinity. Well, what that's equal to is we've got 1/2 over 1 minus 1/2, which is equal to a half divided by a half, which is equal to 1. So there you go, Zeno. You can walk across the street. You just need a little bit of calculus. And honestly, this isn't even really calculus. This is just algebra. So let's talk just a little bit more about this little condition here, the requirement for convergence, because this is probably one of the bigger mistakes that people make when it comes to testing for convergence. So so have you guys talked a little bit about like if and only if statements, or like, no? Okay. So I want to talk a little bit about if and only if statements. So this is something that I'm hoping will stick with you for the rest of your life, because it's a huge misconception in logic that, like, I can't even begin to tell you how many adults make these mistakes, and it's not just about mathematics. It's about like navigating the world that we live in. We live in a very logical world, right? Most of the time, especially in a legal sense, right? There's lots of laws, and laws require an understanding of logic. So we should talk a little bit about if and only if statements. So I'm just going to illustrate this with a few examples. So go ahead. Okay, let's do those examples then. Okay. Say that one more time. Okay, so you work in a bar. Okay, so you want to make sure nobody underage is drinking. Okay, so 4 people. I'm just going to draw 4 people. Yeah. Yeah. Okay. So the ginger ale and the vodka. So I would want to check the person who's drinking vodka. Yeah. Yeah, because I don't care if anyone's drinking ginger ale. You're fine to drink ginger ale. It doesn't matter what age you are. But if you're drinking vodka, I should check your ID for sure. Mm-hmm. Well, I would want to check the 16-year-old. Yeah, I don't care about the 31-year-old. Absolutely. Mm-hmm. I'm not sure if I do. Why don't you tell me? Okay. I have heard this one, yeah. Okay, so if there's a vowel on the card, there has to be an even number. Yeah. Okay, so we've got 4 cards, and I want to prove that this rule is true for all the cards. Mm-hmm. Yeah. Yeah, so I need to ensure that if there is a vowel, then there is an even number. So yeah, I think that often people think that these both have to occur at the same time. But the only thing that you need to really care about is that if there's a vowel, if there's a vowel, then you need to double check that there is an even number on the other side. So certainly we would need to check this one, right? Because there's going to be a vowel there. So we want to make sure that there's an even number on the other side. This one we don't care about, right? Yeah, you don't care about the 31-year-old. Yeah. So yeah, it doesn't matter that it's not a part of our rule. Doesn't have a vowel. But yeah, I think where you're going with this is that people get this part mixed up. Which one of these cards do you choose? And you might think, okay, well, if there's a vowel, then there has to be an even number. Therefore, I should check this one, right? Because it's got an even number. So there should be a vowel behind it. But that's not what the rule is. The rule doesn't say anything about what happens to even numbered cards. It only says what happens to cards that have a vowel on one side, right? So the one we actually have to check is this one, right? Yeah, we have to check this one, because if this one has a vowel, behind it, then that means our rule is broken, right? But I mean, it doesn't matter. Like maybe this one has a consonant behind it, right? And that doesn't matter. The card does like if it has a vowel or a consonant behind it, that doesn't matter, right? All that matters is that the cards with a vowel on them have an even number associated with them. Yeah, I really like that example. Yeah, so another, and I think that the best way to learn about like conditional statements is just through examples. One that always sticks with me is that so let's see here. I don't always like using this example because it's you know, people can misinterpret it as maybe being like sexist or like something about religion, but it's just one that sticks with me, and I'm just gonna give it to you anyway. So just please don't complain about it. So one is that, so if you are the Pope, then you are male. It's a fact. It's part of the Catholic Church that the Pope has to be a male. So if you are the Pope, you have to be male. But it is not also true that if you are male, then you are a pope. You are the pope. Maybe you are. Exactly, yeah. So there's like a whole algebra of logic that you can start playing with. So what Maya was talking about was called the contrapositive, which is an equivalent statement, but it's kind of reversed. So you can sort of reverse both of the statements. So you reverse the order of the statement, and you also change the truth value of both of those statements. That's called the contrapositive. So you could say, if you are not male, then you are not the Pope. That is true. So these two statements are exactly the same statement. They mean exactly the same thing. They are true exactly the same time. Whereas this second statement here, this one is absolutely false, right? There's many counter examples, right? I'm male. I identify very much as male, and I'm certainly not the Pope. So so that's my little quick. I'll get back to you on that. I'm not wearing the hat, so maybe that's enough for you. So that's my little quick lesson on logic. It's important to know that, because our rule, remember that our rule is if the series converges, the series tends to 0. Okay? So in other words, if the sum, where n goes from 1 to infinity, of an, I meant to say sequence. Sorry, thank you. So if an is equal to some kind of, let's call it L, like some kind of limit. So if there is a well-defined, and I'll say that, why don't we say if it's a real number, okay? Because in positive and negative infinity, those are not real numbers. So if the infinite sum is a real number, then the limit as n approaches infinity of a sub n must be equal to 0. However, so this is true. This is also true. Okay, so this part is true as well. So if the limit as n approaches infinity of a sub n is not equal to 0, then the sum, where n goes from 1 to infinity of an, is not a real number. So it diverges. So I'll just say i.e. diverges. And then over here I'll say i.e. converges. Okay? So this is a very quick test to tell when a series diverges. It's a great way to say, okay, well, I wonder if this series converges or diverges. Boom, the limit is not equal to 0, therefore the series diverges. This test has nothing to do with convergence. It tells you nothing about it converging. It will only verify that it diverges. So I'm going to write a false statement. A false statement is, so I hesitate to write false things down, because sometimes people write stuff down and they don't write that it's false. So be aware, this is absolutely a false statement, that if the limit as n approaches infinity of an equals 0, then the sum of an converges, i.e. converges. This is not true, okay? This is absolutely wrong, okay? And there's a great example of this. Remember that this is a sum. This is a sum, So we're saying if this converges, like let's say that we've got an infinite sum. Like imagine what these terms are looking like, these an terms. If we're adding a whole bunch of numbers, like an infinite number of numbers, right? At some point, if it's gonna like converge to a real number, we're gonna have to be adding very small numbers, like numbers that are so infinitesimal that you can't even see it grow, right? So like that's equivalent to saying that the limit as n approaches infinity of those terms, like the sequence, those have to tend towards 0, okay? But the converse, no, this one is about, yeah, this is about converging statement series. Okay, so it's basically saying if your series converges, then the limit of your terms is equal to 0. Like you're approaching 0. Your terms are getting smaller and smaller and smaller until finally they get to 0. However, the second one is about divergence. So if your terms do not end up going towards 0, like maybe they end up going towards 0.1, right? A very small number. But if you add 0.1 to itself infinitely many times, then you get infinity, right? And then the big one is that this is a false statement, and it's confusing to think of an importance, like a false statement, as being important. But this is important because everyone tends to get this one wrong. So it is important to study it and say, okay, this is a false statement. So if, like, let's say that we can come up with a sequence that tends towards 0, like the limit of this sequence goes towards 0. If we add them up, does that end up equaling anything meaningful, or does it diverge? Well, let's look at the harmonic series. Yeah, the harmonic series, very famous series, and it's probably the most straightforward series that you could imagine. So the harmonic series is the sum from n equals 1 to infinity of 1 over 2 to the n. Or wait, no, sorry, that's not it. That actually does converge. It's 1 over n. 1 over n. So it looks like 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus, and it keeps on going and going and going. Now, these terms tend towards 0. As we get further and further along, we're getting closer and closer to 0 every time. However, and I realize we're going over time here, so I'm going to wrap it up in a second. This series does not converge. Okay, this series diverges. This series diverges. Was it on Khan Academy? Oh, nice. So yeah, I want to go over this proof. The proof that I know, it requires the comparison test. But I don't want to talk about the comparison test because I do have to prepare for my grade 11 class, which starts in about 20 minutes. So I'm going to leave it there for today. I think it's been a while since I've assigned any homework, so I think we should probably get on that. So let's do a few questions from 11.2. 11.2. Okay. Let's do questions 1 to 10. Okay? Questions 1 to 10. So your homework is questions 1 through 10 on section 11.2. So we'll do more of them as we progress, but it's important to actually start practicing some of these. And they're not too bad. But yeah, it's important that you actually try some of these out for yourself. And I think that pretty much does it. So tomorrow we'll talk about the comparison test. The comparison test, I think I mentioned this yesterday, is not in your textbook. So I'm just going to share it with you because it's a really important test. It's also like the easiest test, as far as I'm concerned, or the easiest to understand. So I think it's important that I share it with you. Yeah, I couldn't find it in your book, so I'll just share it with you. We probably won't get to practice it because if it's not in your textbook, then there probably won't be any questions that require it. But it's still a good thing to know and just something to have in your little mathematical tool belt. Anyway, yeah, I'll sign out now. Sorry for going over, but I'll talk to you guys tomorrow. Okay, bye bye.